This is a model that I made to emulate intelligent slime and apply it to the problem of portfolio optimization. I did it for a mathematics unit at university, and I wanted to combine my passion for finance with my passion for maths. So in this, the white pixels are stocks and the green stuff is slime, and you can see the slime congregates around stocks that it chooses. The concentration of slime around specific stocks at the end of the simulation determines the weightings of those stocks in the portfolio, and we can measure the efficiency of a portfolio using the Sharpe Ratio, which I'll talk about in a bit. This Jupyter notebook can be found on my GitHub, which is in the description, but basically it's the whole assignment going through explaining the problem, the theory of optimization problem, and how I implement the problem with the slime model. So the hardest part of this model is figuring out how to implement the problem of portfolio optimization in the slime model. Now, there's three main parameters that govern the problem of portfolio optimization, and the hard part was figuring out how to implement these three parameters in my slime model. To outline the portfolio optimization problem, if you have one stock, that stock can have an expected risk and an expected return. Now, in theory, the expected return is taken as historical returns, and the expected risk is taken as historical variance in a stock, so how much it changes. And the aim of the problem is to build a portfolio of multiple stocks, in this case 10, that gives maximum return to the portfolio and minimum risk or minimum variance, minimum swings in the portfolio. The three parameters are the expected return of an individual stock, the variance or risk of an individual stock, and the covariance between stocks, and that is how they move together. Say two stocks like Pepsi and Coca-Cola, they're under the influence of the same macroeconomic trends, and they'll tend to be somewhat correlated. What you want in portfolio optimization is high expected return stocks, low risk stocks, and stocks with low correlation. And that's because you want the swings of the stocks to even out so the overall risk of the portfolio is minimal. So if you want to read through this, I go through setting up the world for the model, and what I do first is I set up a 50 by 50 grid and represents the stocks on a 2D grid. Now here I have the covariance matrix, and I use multi-dimensional scaling to represent the covariances as two-dimensional distances between stocks. That is, two stocks that have a low covariance that move differently will be closer together because we want slime to be attracted to both of them at the same time. I should mention that I'm using the top 10 stocks on the ASX to build my portfolio, that is the biggest companies listed on the Australian Stock Exchange, and I'm taking the assumption that the expected risk and returns of these stocks is equal to the historical daily returns from the past year. We talked about representing the covariance parameter in the model, and now we'll talk about representing the expected return and expected risk of stocks. Here I've set up fields that basically determine how much the slime is attracted to certain areas and repelled from certain areas. So this represents the expected return field. Whiter areas are stocks with higher expected returns, and I make a field so that slime close to these stocks is attracted more or less to areas of high expected returns. And I do the same for expected risk. Areas and fields with more blue is more repulsive for the slime. So slime is repelled away from stocks with a higher risk and attracted to stocks with a higher return. And those three parameters, together with the randomness of slime to represent the slime exploring different territory, represents the model in full. Quickly explaining the Sharpe Ratio, it's basically a measure of the risk-adjusted return for a portfolio. So it takes in the return of the portfolio, takes away the risk-free rate, which is the rate of return you can get for no risk and divides it by the risk of the portfolio. So it's basically the return over the risk of a portfolio. Then I move on to parameter analysis. So in this part, I analyze the different parameters that can be changed. I take parameters that give better Sharpe ratios, that is a better, more efficient portfolio optimization model, and also parameters that give low standard deviation in results. I want a low variance in the outcome of the model. So the first parameter I test is the number of frames, that is the length of the model. I wasn't sure how long to run the model and when the model really finishes. This is a kind of weird graph and I explained that in my discussion, but I ended up choosing 70 frames for the length of the simulation. The next is the power parameter, and this is a parameter I had to introduce. The probability that slime moved to one of the 8 pixels around its neighborhood was very similar for each of the 8 neighboring pixels. And so I introduced a power parameter and then normalized the probabilities so that I could govern the randomness factor in where the slime moves. So basically a lower power parameter means more randomness and a higher power parameter means less. And so tuning this parameter, I found that a power value of 80 gave the best Sharpe ratio and the lowest standard deviation. Next, we tune the alpha parameter, which is basically your investor sentiment, and this is quite an important parameter. It determines how much the slime is attracted to stocks with high expected returns versus repelled from stocks with high risk. A risky investor sentiment cares only about stocks with high expected return and doesn't care about risk, whereas a conservative investor sentiment cares more about the picking stocks with lower risk than stocks with high expected returns. And so I can tune this parameter between 0 and 1. And what was really interesting is plotting the Sharpe ratios from the different portfolios. This is 20 different portfolios from an alpha of 0 to 1. And you get the efficient frontier that comes out of modern portfolio theory. And that is each portfolio represents a different risk sentiment, and these are the optimal portfolios for that specific risk sentiment. It was really interesting to get this. And another interesting thing that I talked about was higher Sharpe ratios came from more risky portfolios. So when we talk about the final results and we think about this problem as a whole, it seems like a kind of pointless or stupid problem because we already have mathematics to optimize this problem, and using those mathematics, the maximum Sharpe ratio you can get with a portfolio of these stocks is 11.88. Now, I was trying to see how efficient I could get this version, this implementation of my model. And after parameter tuning, the best I could do was a Sharpe ratio of 7.37, which is pretty good. It's like a pretty efficient portfolio compared to the optimal portfolio. But obviously it's not perfect because there's many ways you could choose to implement this model. In whole, this implementation of this model was really rewarding. No one's done anything like implementing a slime model to this area of finance before, this area of financial theory. It was an interesting implementation, and I loved doing work in a new area with no help and trying to figure out how to implement this idea that I had in my head. You can read it if you want, it's in my GitHub, but if you stayed this long and you find this interesting too, you're probably rare, and I thank you for watching. But I think showing your work is a good idea, and this is stuff that I find interesting, so I thought I might as well share it. And if you are also interested in it, then feel free to reach out. I love talking about this kind of stuff. Thanks.